In October 2017, an astronomer in Hawaii was reviewing images from one of the world's most powerful survey telescopes when he noticed something that should not have been there. A faint streak, moving way too fast. Robert Weryk was working with the Pan-STARRS 1 telescope at Haleakala Observatory on the island of Maui when he spotted an object racing across the sky at 6.2 degrees per day. For context, a typical asteroid barely crawls by comparison. This thing was booking it. And when Weryk cross-referenced his data with images from the night before, the trajectory became clear. Whatever this was, it was not from around here. Within days, every major telescope on the planet was pivoting to track it. And what happened next became one of the strangest classification scrambles in the history of astronomy. It was initially given a cometary designation, C2017 U1, because objects on trajectories like this are usually icy bodies from the outer solar system. But then deep images from the European Southern Observatory's Very Large Telescope in Chile revealed something bizarre. There was no coma, no fuzzy halo of gas around it, no tail, nothing. This thing looked bone dry, so they reclassified it as an asteroid, a 2017 U1. But here's where the real shock landed. When scientists calculated its orbit, they found an eccentricity of 1.20. Anything above 1.0 means an object is not gravitationally bound to our sun. It is passing through. This was not an asteroid from our solar system. It was not a comet from the Oort cloud. This object had traveled across interstellar space from another star system entirely and just happened to swing through our cosmic neighborhood. On November 6, 2017, the International Astronomical Union did something they had never done before. They created an entirely new classification, the letter I for interstellar, and officially designated this object 1I 2017 U1. The Pan-STARRS team, consulting with Hawaiian language experts Kayu Kimura and Larry Kimura, named it Oumuamua. In Hawaiian, that roughly translates to a messenger from afar arriving first. And that opening character is not an apostrophe. It is an okina, a Hawaiian glottal stop. So if you have been saying it wrong this whole time, now you know. To understand how dramatic this flyby actually was, let's talk about the trajectory. Oumuamua came screaming in from the approximate direction of the constellation Lyra at 26.4 kilometers per second. It swung around the Sun on September 9, 2017, passing at just 0.255 astronomical units from our star. That is closer than Mercury. At that point, it was moving at 87.3 kilometers per second. That is roughly 196,000 miles per hour. Then it whipped past Earth on October 14 at a distance of about 24 million kilometers. And here is the frustrating part. Nobody noticed it until 5 days later. By the time Weryk found that streak on October 19, Oumuamua was already heading for the exit. The total observation window lasted about 75 days. By early January 2018, the Hubble Space Telescope captured its final images before the object faded beyond detection. As one NASA scientist put it, this one is gone forever, and most of what we will ever learn about it had to come from those brief weeks of observation. So what exactly did we learn in those 75 days? Well, every single measurement came back weird. The light curve, which is the pattern of brightness changes as the object tumbled through space, showed variations of up to 2.5 magnitudes. That means its brightness fluctuated by a factor of roughly 10 as it rotated. To put that in perspective, that was one of the most extreme brightness variations ever observed for any small body in our solar system. And it implied an absolutely extreme shape, with an axis ratio of at least 6:1. The first interpretation was a cigar shape, roughly 800 meters long by 80 meters wide, and the European Southern Observatory released that now famous artist's illustration of a long, reddish, tumbling rock that looked like something out of a science fiction film. That image went everywhere. But in 2019, researcher Sergei Mashchenko ran hundreds of millions of shape simulations and found that a cigar was actually the less likely option. Some later studies suggested the data might better fit a flattened, pancake-like disc shape, roughly 115 by 111 by 19 meters. Think less interstellar cigar and more cosmic frisbee. Either way, nothing in our asteroid or comet catalogs comes remotely close to that kind of elongation. Typical elongated objects in our solar system rarely exceed a 3:1 ratio. On top of that, Oumuamua was not spinning cleanly. It was tumbling chaotically, rotating around multiple axes at once, with apparent periods of about 7.4 and 7.9 hours interfering with each other. Astronomer Wesley Fraser and his team calculated that the damping timescale for this tumble exceeded 1 billion years, meaning whatever set it spinning like that probably happened back in its home star system, and it has been tumbling through the void ever since. The surface was reddish and spectrally featureless, consistent with compounds called tholins, which are organic molecules that form when cosmic rays bake simple chemicals over millions of years. So the color made sense for something that had been drifting through interstellar space for a very, very long time. But perhaps the most baffling thing about Oumuamua was what it did not do. Despite passing closer to the Sun than Mercury, at temperatures that should have cooked volatiles off any icy body, deep imaging from the Very Large Telescope, the Gemini Observatory, and the Spitzer Space Telescope found absolutely nothing. No coma, no tail, no dust emission, no detectable outgassing of any kind. By every visible measure, this looked like a completely dry, bare rock, and that would have been strange enough on its own. But then came the discovery that turned the entire scientific community upside down. On June 27, 2018, a team led by Marco Michelli published a paper in the journal Nature that dropped a bombshell. Oumuamua's trajectory showed a non-gravitational acceleration, and it was detected at 30 sigma confidence. In science, 5 sigma is considered rock-solid proof. 30 sigma means there is essentially zero chance this was a measurement error. The object was speeding up as it left our solar system, and the Sun's gravity alone could not explain it. The measured acceleration was about 5 times 10 to the minus 6 meters per second squared at 1 astronomical unit from the Sun. The total excess velocity amounted to roughly 17 meters per second. That might sound tiny, and it is compared to the object's overall speed, but it was unmistakable in the data. Now, for regular comets, this kind of acceleration is completely normal. Ices sublimate near the Sun, they create little jets, and those jets push the comet slightly off course. Micheli's team acknowledged this was the most physically viable explanation. But the explanation came with serious challenges. There was no visible coma, no dust, no water vapor. It would require an unusually high gas-to-dust ratio, far beyond what we typically observe in comets. On top of that, physicist Roman Rafikov showed that if asymmetric outgassing was really happening, the torques on such an elongated body should have significantly altered its rotation, possibly even destabilizing it. But Oumuamua's rotation stayed remarkably stable. So now the scientific community was staring at a genuine paradox. An object that accelerated like a comet, but looked absolutely nothing like one. And this is where things got really interesting, because the race to explain what happened split the astronomy world into competing camps. The first major attempt came from Daryl Seligman and Gregory Laughlin in 2020, who proposed that Oumuamua might be a hydrogen iceberg. Molecular hydrogen freezes at about 6 Kelvin, which is absurdly cold. Their idea was elegant. As the hydrogen sublimated near the Sun, it would produce thrust while being completely invisible to our telescopes. The erosion would even explain the weird shape. But Thiem Huang and Avi Loeb published a rebuttal showing that a hydrogen iceberg could not survive the interstellar journey. Starlight between the stars would evaporate it long before it ever reached our solar system. So the idea quickly lost favor among many researchers. Then Stephen Desch and Alan Jackson at Arizona State University offered a different exotic ice in 2021, solid nitrogen. Their model proposed that Oumuamua was a chunk knocked off a Pluto-like world in another star system during some kind of dynamical upheaval. Nitrogen ice has a high albedo, about 0.64, similar to Pluto's surface. That meant the object could be much smaller and lighter than previously assumed, roughly 45 by 44 by 7.5 meters, making even modest nitrogen sublimation enough to explain the acceleration. They framed it beautifully as potentially the first sample of an exoplanet delivered to our doorstep. But critics questioned whether nitrogen ice fragments would be common enough in the galaxy for one to be our very first detected interstellar visitor. Meanwhile, another group took a completely different approach. Researchers including Amaya Moro-Martin and a team from the University of Oslo proposed that Oumuamua might be an extremely porous fractal dust aggregate, basically a cosmic dust bunny with a density about 10,000 times less than water. At that extreme porosity, pure sunlight pressure could push the object without needing any outgassing at all. The physics appeared to work under certain assumptions, but nobody has ever observed a macroscopic object that fluffy, and it is hard to imagine something that fragile surviving a trip between the stars. And then there was the hypothesis that made international headlines and started one of the biggest scientific debates of the decade. In November 2018, Harvard astronomer Shmuel Bialy and Avi Loeb published a paper in the Astrophysical Journal Letters arguing that if Oumuamua had an area-to-mass ratio implying a thickness of less than a millimeter, then solar radiation pressure would perfectly explain the observed acceleration. And since no known natural process produces objects that thin and that large, Loeb proposed that Oumuamua could be a light sail, debris from an alien civilization's technology drifting through interstellar space. Now, Avi Loeb is not some random guy on the internet. He is the Frank B. Baird Jr. Professor of Science at Harvard. He chaired Harvard's astronomy department for nearly a decade. He has published over 700 papers and serves on the advisory board for Breakthrough Starshot, the real initiative to send tiny light sail probes to nearby stars. So when he said we should consider an artificial origin, people could not just wave it away. Loeb pointed to a stack of anomalies. The acceleration followed an inverse square law, exactly what you would expect from radiation pressure on a thin surface. The object entered our solar system at a velocity remarkably close to the local standard of rest, a kinematic signature shared by fewer than 1 in 500 stars. Combined with the extreme shape, the high reflectivity, and the complete absence of outgassing, Loeb argued that the combination of anomalies could be consistent with a technological origin, and that dismissing the possibility outright was intellectually dishonest. He wrote a best-selling book called Extraterrestrial and compared the stigma around discussing alien technology to the resistance Galileo faced centuries ago. The scientific community pushed back hard. A team of 14 astronomers published a comprehensive review in Nature Astronomy, concluding that the observations were consistent with a purely natural origin. Karen Meach, who led the original discovery team, asked bluntly why you would jump to the most extreme explanation. Jason Wright at Penn State, himself a SETI researcher, co-authored a detailed rebuttal, concluding there was little to no evidence for an artificial origin. Critics also pointed out that Loeb's extensive media campaign, over 2,000 interviews, created a misleading public impression of where the scientific consensus actually stood. But here is the thing. While everyone was arguing about aliens versus nature, the most elegant explanation might have been sitting right under their noses. In March 2023, Jennifer Bergner at UC Berkeley and Daryl Seligman at Cornell published a paper in Nature that required nothing exotic at all. Their mechanism was beautifully simple. During Oumuamua's long interstellar journey, cosmic rays penetrated deep into its water ice and converted a portion of the water molecules into trapped molecular hydrogen through a process called radiolysis. This has been documented in laboratory experiments since the 1970s. As the object warmed near the sun, the amorphous ice restructured and released that trapped hydrogen gas, producing an invisible thrust without sublimating the ice itself. No dust, no coma, no visible outgassing, just hydrogen quietly escaping from rearranging ice crystals. The beauty of this model is that it requires nothing more than ordinary water ice and cosmic ray exposure, two things that are literally everywhere in space. Loeb and Huang challenged the thermal modeling, and another team questioned whether the hydrogen yield would actually be sufficient. The debate continues. But as of right now, this has emerged as one of the most compelling natural explanations so far. And while that debate was playing out, something remarkable happened that reframed the entire Oumuamua story. By December 2024, Seligman and colleagues had identified a growing number of objects in our own solar system showing similar behavior, objects with non-gravitational accelerations and no visible outgassing, in some ways reminiscent of Oumuamua. Scientists nicknamed them dark comets. And just like that, Oumuamua went from being a bizarre, inexplicable anomaly to a potential prototype of an entirely new class of objects that had been hiding in our own backyard this whole time. If you are enjoying this deep dive into one of the biggest mysteries in modern astronomy, hit subscribe. We cover stories like this every week. Now, Oumuamua was just the beginning. In August 2019, amateur astronomer Gennady Borisov discovered the second confirmed interstellar object using a custom telescope he built himself in Crimea. Unlike Oumuamua, Comet Borisov looked like a perfectly normal comet, complete with a coma and tail. It contained cyanogen gas, carbon dioxide, and water. Standard stuff. The contrast between the two visitors immediately showed that interstellar objects come in very different flavors. Then in July 2025, the Atlas telescope in Chile found the third one. 3I Atlas came in with a record-breaking orbital eccentricity of 6.14 and an incoming velocity of roughly 60 kilometers per second. It showed clear cometary activity with a massive coma stretching over 26,000 kilometers across. And this time, the scientific response was on a completely different level. Hubble, the James Webb Space Telescope, Parker Solar Probe, Europa Clipper, Lucy, Psyche, and multiple ESA, Mars orbiters all turned to observe it simultaneously, an unprecedented multi-mission response that showed just how far our detection and response capabilities had come since Werik spotted that faint streak in 2017. The infrastructure for catching future visitors is only getting better. The Vera C. Rubin Observatory in Chile achieved first light in June 2025, and its record-setting 3.2 gigapixel camera discovered thousands of new asteroids in just its earliest test observations. Once its full survey begins in 2026, projections suggest it will detect 1 to 2 interstellar objects per year. And ESA's Comet Interceptor mission, scheduled to launch around 2029, will park at a gravitational sweet spot in space and wait for a suitable target to chase down, potentially including an interstellar visitor. So what does all of this actually mean? Oumuamua showed us that our solar system is not isolated. Estimates suggest there could be thousands, possibly tens of thousands of interstellar objects passing inside Neptune's orbit at any given moment. Each one is a message in a bottle from another planetary system, carrying information about how other worlds form, what they are made of, and how their stars shape them over billions of years. We still do not know exactly what Oumuamua was. The trapped hydrogen model is the best natural explanation we have, but the question is not definitively closed. What we do know is that its brief visit changed astronomy forever. It created an entirely new field of research. It spawned dedicated missions and detection systems. It revealed dark comets hiding in our own solar system. And it forced the scientific community to reckon with a humbling truth. Sometimes the universe sends you something you were not expecting, and 75 days is not nearly enough time to figure it out. Oumuamua is still out there right now, tumbling through the darkness at 38.3 kilometers per second. It is expected to pass beyond the outer boundary of the heliosphere sometime in the late 2030s, leaving our solar system's domain for good. A messenger from afar that arrived first, spoke in riddles, and made absolutely sure we would be paying attention the next time something comes knocking. If this story blew your mind, you will definitely want to watch this next video about the most terrifying discoveries scientists have made in deep space. Trust me on this one. See you there.